So what we are going to do is, so I yesterday we are going to start with quantum mechanics. So the book which we are going to is Eugene Merz Becker. So what we are going to do, we are going to have chapter 1, 2, 3, 4, 5. So these we will do in detail way, and chapter 11 and portions of these chapters which will intersect with yourselves. These we will do in some detail. The 3 chapters will do what are the portions which are relevant to yourself. So what we are going to see is the chapter. So introduction to quantum mechanics. So quantum mechanics. So if I just say if I use the words of the book, quantum mechanics is a theoretical framework in which it has been possible to describe, correlate, and predict the vast range of physical systems, which includes from particles to nuclei, atoms, and radiation to molecules and condensed matter physics. So as such, the quantum mechanics as such is a very fundamental field. It will describe whole of nature in principle. But if you want to concretize it, if you want to make it more relevant, so that theoretical framework, in this theory, we can describe, correlate, and predict. We not only can describe, we can relate phenomena, and we can also predict things. Things about what? About physical systems. And physical systems are what? They may be particles, they may be nuclei, they may be atoms, they may be radiation, molecules, or condensed matter physics, which you normally call solid state physics. So you see, the range of quantum mechanics is very huge. Huge in what sense? So it explains a lot of things which we are going to say. So in your condensed matter physics, condensed matter physics, वो physics which we study many electron physics, solid state physics की एक higher form. The theoretical foundations of solid state physics, उसी को हम condensed matter physics कहते हैं. So the point to say is that historically, if you know, there is a so there is a history to it, which you might have been reading in earlier classes. So people first believed in waves. They had a particular corpuscular theory of light. Then they shifted to wave theory of light. Then they said that no, there is something called wave-particle duality. So light not only has a wave behavior, it has also particle behavior. So we say that wave-particle duality. Sometimes it behaves as wave, but then this understanding was later extended also to particles also too, not only for photons and lights, but matter in general, which was called de Broglie's relation or wave equations. So historically, if you see, there are two ways of studying a subject. One is historical way, how it has, this is known as historical way. The another is the conceptual or logical way. It's not necessarily how a subject evolves historically. It is the most natural or logical way of describing the subject. But since we are studying the introductory part of it, so it's better to have a historically also how the subject has evolved. Just like in a movie, hai na? You see actors, these are characters, so you can also see him. So how the subject, a theory describes this thing, who were the people, who were the physicists involved, what were the earlier ideas, some of the ideas were correct, some were partially correct, some were modified. So what we have as a crystallized understanding now, which we call quantum physics, it was not always like that. It gradually evolved. Some scientists believed in one way, some believed in different ideas. Some ideas were correct, some were partially correct, some were done away with. So we'll have a glance over how it has historically it also had developed. That's our main. So in that sense, for example, there have been some fundamental equations like E is equal to h nu. This has been Planck's relation that things come. This is an elementary quantum of action. So this is frequency. So yesterday also when we make transition from classical to quantum, one way of looking at classical is that in a classical way we can a quantity can take any values, infinite values. But once we go to quantum mechanics, it will only take discrete values, and those discrete values can be seen from this. This is one of these things will only take discrete values as a multiple of this thing, and that's a Planck constant. Any frequency, any transfer of energies between atoms, electrons, in terms of radiation, it can exchange only by some discrete amount multiplied by this elementary quantum of action, which is also called as Planck's constant. So frequency transfer. So how two atoms, two electrons, they relate with each other via radiation. One photon, or there is an electron goes from one state to another state, there is a jump. In earlier classical radiation theory, what was this thing? The electrons should continuously, once it will radiate, ultimately it should lead to. So it could not explain the stability of atoms. So that's why Bohr came up with quantization rules, that somewhere in some orbits there should be some stability, and that stability also can be, basically there are some discrete orbits in which these electrons are supposed to lie. That's it. And if you just see Bohr's initially there he used canonical variables pi and qi. So he just the initial way of writing, Bohr's way of writing was this: pi qi is equal to pi dqi is equal to nih. So these are P and Q. P is the position, Q is the momentum. These are the variables in classical mechanics. What Bohr showed is that Pi dqi is equal to nih, where ni are integers and so its momentum, its position, so it's on the closed initial orbit, closed orbits for Bohr. But it was shown to be true for simple atoms, this equation, this thing. For more complex atom, helium atom and other things, this equation did not hold. That's the point. That's the point. So it's partially, it was shown as a part of history. And if we just see it in terms of, if we want to extend the other equation, when we extend the de Broglie equation to matters. So we say lambda is equal to h over mv or h over p. So when the masses of the particles become very heavy, this wavelength becomes appreciably small. That's why we are not able to observe matter waves generally. So it's more pronounced or more appreciable in when we go to subatomic particles. So it can be explained from this, and we can also calculate the wavelength of. So if we want to have, for example, if we want to be show that in a certain distance, you want to compare the motion of the particle which is moving with vis-a-vis the space in which it is moving. So what is the ratio of momentum and that space in which it is moving, such that we will be able to observe this de Broglie wavelength. So if it's like this, if lambda by x is basically what? Its wavelength, it's the size. So it will be h over x into x over. So so normally it will come out to be very less than 1, because at higher velocities, at higher masses, and the masses will become very large. So the quantity in the numerator will come out to be small. But the point is, if we make a quantity, if we make this comparable to this thing, then if xp is very greater than h. So this is the condition for the classical mechanics. Classical mechanics means the particle which we observe, the large scale body, atom, this earth, moon, this bag, human beings, and they are large. So that thing, this is, when it's comparable, you can go to those subatomic particles where you can appreciate it. For example, a typical value of, for example, so atom which is moving, if we go to the book which has a temperature of this Kelvin, wavelength will be 10 to the power minus 6 meter. Both common, it's very small, 10 to the minus 6 microns. It's very small, 0.0000. But the point is to mention. So now there is something called have you heard of correspondence principle? Correspondence principle. So there's a classical proof. It's also going to be classical quantum analogues. This was first articulated by Bohr. So how? So in the limiting case, the quantum mechanical, when the classical systems are classical, and when in the limiting cases of quantum mechanical systems, we can have classical systems. You got the point. So there is a particular way. So this says that classical mechanics is not only valid, but quantum mechanics under suitable limits should reproduce classical mechanics. So if quantum mechanics is the ultimate theory, okay, for approximations where xp is greater than h, we take classical limits. But under suitable limits, classical mechanics will be a suitable approximation of quantum mechanical theory. So this is the point. So in physics, you can, typical cases, WKB approximation, which you might study in that thing. Now the question is, this is known as correspondence principle. The other is something called complementarity principle. Have you heard? So before we are going to say about complementarity, so we say what is wave function and its meaning. Because there are some puzzling ideas here. For example, when we say that particle is having both particle nature as well as wave nature. So you can say, for example, wave what is the fundamental property of wave? Wave का ये है कि it dissipates, it somehow delocalized. Wave has a delocalization. So it will not remain, so wave, it's a sort of disturbance switch. It's a longitudinal wave, stationary wave, water wave, spheric, which are waves these are, electromagnetic waves. It doesn't remain, this disturbance passes. For electromagnetic waves in vacuum. But when we talk of particle, it's localized. We talk of waves also, there is a oscillation of particles, but the disturbance moves, particles oscillate at their own position. So these are two somehow contradictory ideas. Are they contradictory or not? So how can a particle be local? When we talk of wave-particle duality, how can it be localized as well as delocalized at the same time? You cannot, it's very difficult to imagine or perceive how can we. And coupled to the fact, हम ये भी कहते हैं कि what we are also further saying that these waves and particles, they have discrete. They will take only values. They will not take all values. They will take discrete values. Got the point? So that even disturbance, जो भी है, whatever that is, that will have some discrete transfer of energies or these exchange interactions in only the discrete amounts. So it's not an easy idea. So you will become gradually, we will not understand it. We will understand it partially. We will become how we can approach it. We will become that with time. We will become more comfortable with the idea. But it, in principle, is a very complex to visualize also. So how do physics? How this difficulty को कैसे articulate किया है? For example, people used to say earlier, physicists जो थे, since we are studying a history of quantum mechanics, when it was developing, the people used to say on Sundays, Max Born, physicist, who used to say on Mondays, Tuesdays, Wednesdays, physicists believe that matter is made of its wave. On Saturdays, Fridays, and Sundays, it's a particle. So he used a term called vehicle. Neither it is wave, neither it is a combination of wave and particle. So the point to mention is that, so for even when it was beginning, it was a complicated, people were not able to understand it. How, if a thing is localized and delocalized, how we can imagine it that way. And this difficulty was articulated with something called complementarity principle, which was invoked by Bohr. What he said that in what is complementarity principle, कि उसमें ये है कि that once we don't say fundamentally whether matter is wave or particle or photon. What we say that in order to describe whether a system is wave or particle, we have to design an experiment, choose an experiment to see it's a particle. If we design an experiment which is shown, we can have wave-like properties. We can design experiment accordingly. If we want to prove that photons are having particles, we can have an experiment like photoelectric effect and other things, Compton effect and other things. You know? So you have to design an experiment specific to what you want to measure. Such that, for example, if you concentrate on wave properties, then particle properties become fuzzy. So in a given experiment, there's an inverse relationship. The more you want to show that electron is a particle, you cannot show in the same experiment it's a wave. The more you want to show accurately it's a wave, the particle nature you are showing, how you can show it becomes fuzzy. The more you will show it's a particle, you cannot show it's a such that they are. So in a way, it's sort of the scientist Bohr. He was also influenced by Chinese philosophy and yin yang. One is maximum, another is minimum. If it becomes maximum, it becomes, or they will become of the same average. It will swing. So in a you cannot design an experiment. You can show perfectly it's a particle or perfectly it's a wave. So if you concentrate on wave, because so basically it's a sort of a particle embedded in a wave. So we say the normal thing is that what Bohr explained, इसकी analogy उसने ली in terms of standing wave. Standing wave क्या है? So you plug it here, there is a node, antinode. So in the same way, in those Bohr orbits, we say that electron is not a one particle, it's a series of particles. So they continuously interfere with each other. So where the interference is maximum, we say probability is there is maximum. There is the concentration. We say it's a particle is there. Presence of electron is there. So that's it. Where it is least, we say it's not there. So this analogy of stationary waves, where these energies can be maximum or minimum at this interference, whatever. So that analogy is also helpful in how we can explain quantum mechanical things, how we can explain nature as quantum mechanical. Means in its ultimate details, जो particles है, electrons, photons, जो भी है, they are a mixture of this wave and particle nature का combination है, sort of. That's it. And coupled to the idea of energy exchange come in discrete amounts. Energy transfers in these come in discrete amounts, and it is inactivated by sort of this complementarity principle. There's एक sentence इसमें है, there this epistemological view of, so epistemological, you know what's epistemological? एक होता है ontology, another is known as epistemology, and the other is known as teleology. We'll leave teleology and ontology. फिलहाल this book has used, so he says that epistemology means episteme, the foundations of knowledge. So foundations of classical mechanics as in the branch of knowledge, and once we make transition from classical to quantum mechanicals. So it's a sort of historical curiosity. You are not that much interested in, maybe it may not, but how the classical way of looking at things and how quantum mechanical way of looking at things. And classical mechanics explains, है ना, celestial system, solar system, जो भी है हमारा जो satellite है, ये सब classical mechanics. But once we apply classical mechanics to microscopic world, it's not applicable. So we need new sort of ideas. So need to go from classical to quantum mechanics, the epistemical transition from classical. So even though it may not be, now people are taking जो quantum physicists हैं, they take it as ab initio. But at least you should be knowing what are the foundations of classical mechanics and what are the foundations of quantum mechanics. Where do they differ and where do they agree? That's the point. And इसी में what we are going to study is Schrodinger equation. Schrodinger equation. Schrodinger wave equation. We are going to study it thoroughly. So Schrodinger wave equation is historically is that it enables us to evaluate proper frequencies or eigenfrequencies of general quantum mechanical systems. So here we are going to say just like आपके पास है ना F is equal to ma, how the particle given a particle and given a force, you should be able to determine where the particle has gone after 5 seconds, 10 minutes, 30 minutes, है ना? So in the same way, उसका analog है when we had these ideas of waves, particle, or somehow in quantum mechanical things. So how we define a system of particles or individual particles? So उसकी जो analogous equation है, that's known as Schrodinger equation. So we'll study in detail, but the thing is that Schrodinger equation enables us to evaluate proper frequencies or eigenfrequencies. So eigenfrequencies we know, which is specific value to it of general quantum mechanical systems. Now quantum mechanical systems have wave properties, particle properties, and the energy exchange comes out in certain discrete amounts or specific amounts. So this is the thing. So we maybe as an introduction in today's class, maybe this is. So the more point to mention is there's a section if you want to study. There's a in volume 3rd of Feynman. There's a good first chapter. If you can read this chapter, there's a sequence to this thing. But the point to mention is also our main aim is also we write here there were particles. So we are interested in psi. Have you heard of psi? It's also called wave function. It's the analogy of, for example, a particle. Particle is moving under a certain force. So here this wave function psi, but this psi is what? It's not particle, it's not wave. It's a combination of particle and wave, an idea. It's a sort of particle embedded in wave. Where the probability amplitude is maximum, we say it is there. And the analogy is handy vis-a-vis how we try to understand stationary waves classically. So this is the state psi. Psi or wave function, how we say it's combination of wave and particle properties as well as the exchange energies of psi comes in form of in some discrete amount. And there is also some fundamental transition or fundamental departure from classical mechanics. Classical in the sense in classical mechanics we also assume implicitly, we don't say it, we assume there is something called determinism. Have you heard? है ना? Aksar of them, when we study classical mechanics, you will determine the equations of motion. Given a particle, given a force, you should be able to know पार्टिकल कहाँ 5 मिनट के बाद, यूनिवर्स कहाँ होगा 5 मिनट्स के बाद. सो दिस इज अ डिटरमिनिस्टिक फिलॉसफी. So here, once we have a wave function, sort of uncertainty, which we will study as an uncertainty principle also, but you will see even the very idea of psi embeds some inadequacy, जो हमने complementarity principle में कहा. If you want to make particle properties more, the wave aspect becomes fuzzy, it becomes less adequate. If you concentrate on wave properties, the particle thing somehow goes thing. So this determinism as a philosophy somehow we have to compromise. एक compromise होगा, हो गया experimental compromise. For example, you say that if I don't have patience, so I can make system classical. I can determine अगर यहाँ जैसे statistical mechanics में we make a compromise. वो कहते हैं there are so many molecules, Avogadro number 10 so we'll say average behavior. But in principle, if we want, we can एक molecule पे भी हम we are going to apply Newton's law, है ना? It's applicable. We will be able to find the trajectory of the particles in principle. But since it becomes more complicated, फिर हम average behavior लेते हैं. This is one thing because of our practical difficulties. But here we don't say that thing. This is determinism. But once we go to this psi function है ना, यहाँ even there also we make some compromise. There also. So it's not deterministic in that classical sense also. So this is the important thing. So which will explain, there are various interpretations of how Bohr explained it, how Bohr did it. So these are the foundations of quantum mechanics, which we can have some ideas we can discuss it. Okay, we'll stop today.